The objective of this module is to explain in detail the concept of random variable and probability distribution as well as other closely related concepts. After having read this lesson, you will learn what is a random variable and its possible types, what is a probability distribution, and what are the features peculiar to discrete and continuous probability distributions. Also, you would learn how are these probability distributions derived and how important characteristics like mean, variance for probability distributions are estimated. And in the end, we would learn what is a cumulative frequency distribution and a joint probability distribution function. So let me introduce these concepts. Random variables and probability distributions are most significant components of the statistical theory. This theory has developed on the foundations of massive research and has great knowledge to extend. Discussion on probability theory is incomplete without understanding what is the meaning of random variable and their types. A random variable is a variable whose value depends on the result of the random event. A random event can have several possible outcomes, corresponding to which there are values that the variable can assume. A discrete random variable may assume only countable values such as whole numbers. The continuous random variables, on the other hand, can assume any value within a given interval. The outcome of flipping a coin or rolling a die is illustration of discrete random variables. Weights of students in a class, the arrival time of trains at a station are examples of continuous random variables. A probability distribution is nothing but a series of the possible outcomes of an experiment and the corresponding probabilities of the occurrence or non-occurrence of each outcome in different trials. These trials or these basic concepts have further extensions primarily in terms of determining specific characteristics like mean, variance. This chapter illustrates the determination of these characteristics for both discrete and continuous probability distributions. The module also acquaints the readers or students with cumulative frequency distribution and joint probability distribution function.
Random variable. A random event can have several possible outcomes which are mutually exclusive. In simple terms, if the value of a variable depends on the outcome of a random event, such a variable is said to be a random variable. It is easy to cite examples of random variables from the real world. For instance, the weight of baggage of passengers traveling in an aircraft, or the commuting time for each employee in a company, or the number of defective pipes produced by a newly installed machinery in a firm. Two types of random variables. Fundamentally, the random variables can be classified into two categories, discrete and continuous. In the case of a discrete random variable, the variable can assume finite values or else can be a part of an infinite space as well, in which case there are countable elements. For example, in a survey of villages of Maharashtra, the researcher wants to count the number of hand pumps per village. A random variable is said to be of continuous nature if the value of random variable lies in an interval. For example, the time that a customer spends waiting in the queue to buy a movie ticket is a continuous random variable. The possible values that the random variable can take can either belong to a single interval on the number line or to a unison of disjoint intervals. The discussion on continuous variables often requires knowledge of integers or integrals and derivatives, specifically in the case of application. Probability of distribution or probability distribution. A probability distribution relates each possible outcome of a given experiment with its corresponding probability of occurrence. The probability distribution of the number of heads on flipping 3 coins is shown in the following table. Table 1, where we have outcomes and probability for the experiment of counting the number of heads on flipping 3 coins. Column 1, outcome, number of heads. Column 2, probability P in the bracket X, Px. In outcome, column number 1, we have 0, 1, 2, 3, and the corresponding probabilities are 1 by 8, 3 by 8, 3 by 8, and 1 by 8. The above table depicts the case of a discrete probability distribution. According to the nature of the random variable in question, there are two types of probability distributions also, discrete and continuous. Probability mass function, PMF, for discrete random variable. A discrete random variable x in the sample space S is the one which assumes each of its values with certain probabilities. In other words, probability mass function PMF for discrete random variable gives the probability that various possible values of x can assume. In the above mentioned example, a coin is tossed thrice, therefore x is equal to number of heads. Possible values of x are then equal to 0, 1, 2 and 3. Our set S is equal to HTT, HHT, HHH, TTT, TTH, THH, THT and HTH. Here probability distribution tells us the probability that is associated with different values of x. The Px denotes the probability taken by various x values. Then the function fx is equal to P or probability capital X equal to xi, for xi is equal to 0, 1, 2, 3. This is equal to 0 if x is not equal to xi. This is a discrete PMF of x, where Px equal to xi is the probability that a discrete random variable x, capital X, takes the value of xi. It can be said that fx be a probability mass function of a discrete random variable if for all values of x, following conditions are satisfied. First, fx is greater than or equal to 0. Second, summation over fx is equal to 1. And third, fx is equal to p in bracket x equal to x. Density function of discrete probability mass function. In this table, we have the values of x ranging from 2 to 12. We have the values of y equal to fx, which moves from 1 by 36 to 2 by 36, so on, up to 6 by 36, and then again 4 by 36, 5 by 36, 3 by 36, 2 by 36, and 1 by 36. On recalculation, these values are equal to 0.03, 0.06, 0.08, 0.11, 0.14, 0.17, 0.14, 0.11, 0.08, 0.06, and 0.03. In this example, X stands for the sum we get on rolling two dice, and Y stands for the probability of getting that sum. Probability distribution of continuous random variable. We know that for any particular value of X, a continuous random variable has a probability of 0. A continuous random variable takes a range of value which may be finite or infinite rather than a particular value. A probability distribution of continuous random variable can be defined as a function fx for any x such that c is less than or equal to d. So probability x is greater than or equal to c but less than or equal to d is equal to integral fx dx, where integral is from c to d. The probability density function of continuous random variable must satisfy following properties. First, fx is greater than or equal to 0. Second, integral of fx dx is equal to 1, which implies that probability x takes the values from minus infinity to plus infinity is equal to 1. The probability that x takes on a value in the interval c to d is the area under the graph of density function and above the interval CD. For example, consider the following density function. Fx is equal to 1 upon 27 x raised to power 3, where x is between 0 and 3, which means x is greater than or equal to 0 but less than or equal to 3. It satisfies the first property of non-negativity of function. That is, fx is greater than or equal to 0 for all values of x in the given interval 0 to 3. And we know that integral of fx dx is equal to 1, which is equal to integral from 0 to 3 of 1 by 27 x raised to power 3 and is equal to 1. Will give the probability that x lies between 0 and 3. If you graph the probability density function of a continuous random variable x, then sometime we wish to compute the probability that the observed value of x will be at most x for some given value of x. Cumulative distribution function for discrete random variable. The cumulative distribution function CDF capital Fx of a discrete random variable x with PDF fx is defined as capital Fx equal to probability that x is less than or equal to a small x is equal to summation of py, where y is such that it is less than or equal to x for any x. Fx is the probability that the observed value of x will be at most x. For example, let S be the sample space and x represent the sum at rolling of two dice. So the different values and corresponding PDF is as. In the first column, we have values of x. In the second column, we have PMF or PX. In the third column, we have CDF or capital Fx. The values x takes are from 2 to 12 and the corresponding probabilities are 1 by 36, 2 by 36, so on up to 1 by 36. And the corresponding cumulative distribution function or capital Fx are 1 by 36, 3 by 36, 6 by 36, so on. And the last value is 36 by 36. This Fx is called the CDF because Fx gives the probability that accumulates by summing up the probabilities. So it is a adding up or summation of all the previous probabilities. Properties of the CDF or capital Fx for discrete random variable. The properties of CDF of a random variable satisfies several properties. First is that this Fx, which is capital Fx, is greater than or equal to 0 but less than or equal to 1. Second, f is non-decreasing, that is, if b is greater than or equal to a, then fb will also be greater than or equal to fa. The third property is that limit of fx is equal to 1 as x tends to infinity, and similarly limit of fx is equal to 0 if x tends to be minus infinity. Fourth property, for any two numbers a and b with a less than or equal to b, probability that x is greater than or equal to a but less than or equal to b is equal to fb minus fa. Cumulative distribution function for continuous random variable. Only one thing that differentiates CDF of a discrete random variable with CDF of continuous random variable is that in CDF of the discrete random variable uses summation sign, and that for continuous random variable we uses integration sign. Rest of the concept remain the same. The CDF fx of a continuous random variable x with density function small fx is therefore defined as fx is equal to probability that capital X is less than or equal to x, and is equal to integral from minus infinity to x of fx dx for x between minus infinity to plus infinity. Properties of the CDF fx for continuous random variable. The CDF of a random variable satisfies several properties. Again, the first property is that fx lies between 0 and 1. It is greater than or equal to 0 and less than or equal to 1. Second, again, that f is non-decreasing, which is that if a is less than or equal to b, then fa is less than or equal to fb. Similarly, the third property is again same, which means limit of fx is equal to 1 when x tends to be infinity, and limit of fx is equal to 0 when x tends to be minus infinity. Similarly, we have the fourth property, which is same again for any two numbers a and b with a less than or equal to b, probability that x lies between a and b, which means greater than a or equal to a but less than or equal to b, is equal to fb minus fa. And the fifth property is that f prime x is equal to fx, which is a small fx, which means if we take the derivative of the cumulative distribution function, we get the cumulative density function. Many of the times, investigator uses more than one random variable in an experiment. For them, we have to consider the joint probability mass function, or also known as joint PMF. Definition. Let x and y be two discrete random variables defined on the sample space S of an experiment. The joint probability mass function fxy, which is small f, is defined as fxy is equal to probability that x is equal to x and y is equal to y, and is equal to 0 when x is not equal to x and y is not equal to y. This gives us the joint probability that x, capital X, takes the value of x, small x, and capital Y takes the value of small y. For example, following table given the joint probability distribution function of the discrete variables x and y. This table tells us that the probability that y takes the value of 1 and simultaneously x taking the value of 3 is 0.1. And the probability that y takes the value of 3 and simultaneously x taking the value of 1 is equal to 0.25. This must satisfy following properties. First, fxy is greater than or equal to 0 for all x and y. Second, summation of fxy over y and x is equal to 1. Third, probability that capital X is equal to small x and capital Y is equal to small y is equal to fxy. Fxy stands for the joint density function. Continuous joint probability distribution function. The joint PDF, which is also known as fxy, of two continuous random variables x and y, is a function which satisfies following properties. Again, they are similar. The first is that fxy is greater than or equal to 0. The second is that integration of fxy dx dy is equal to 1, where integration is from minus infinity to infinity over both x and similarly over y. The third property is that the integration of fxy dx dy over a to b and c to d is equal to probability that x lies between a and b and y lies between c and d. In relation with the joint probability distribution function fxy, fx and fy are called marginal probability density functions. The marginal probability density function for a discrete random variable x and y can be expressed in the following manner. Fx is equal to summation of fxy over y and is known as marginal probability density function or PDF of x. Similarly, Fy is summation of fxy over x, which is marginal PDF of y. For example, using the following table to find out the marginal PDF for a discrete random variable or random variables x and y, we have the table where the values of x and y are given. If you add the probabilities over the rows, we get summation of fxy over y, and this is fy. Similarly, summation over columns gives us fx, and we have these summations given in the last column as well as the last row. Let's calculate the marginal PDF of x and y. So fx equal to minus 3 is equal to summation of fxy over y, and this is when we add all these values of 4 by 32 plus 2 by 32 plus 2 by 32 plus 8 by 32, and we get the value 16 by 32. This is the summation over first column. Similarly, we have the summation over the second column, which gives us fx equal to 0. We similarly obtain fx equal to 1 by adding the or summing over the next column. And similarly, when we add over the last column, we get fx equal to 3. These values are, as you can see, 8 by 32, 4 by 32, and 4 by 32. Similarly, we can find out fy is equal to minus 3, which will be equal to fxy over summation over x. And this is again the sum of the elements in the first row, which is 4 by 32, 2 by 32, 1 by 32, and 1 by 32, and we get 8 by 32. Similarly, we can find out fy equal to 0, fy equal to 1, fy equal to 3, and we have the values 8 by 32, 4 by 32, and 4 by 32. The marginal PDF of a continuous random variable x and y can be expressed in the following manner. Fx is equal to integration of fxy over dy. The range is from minus infinity to infinity, and this gives us marginal PDF of x. Similarly, fy is integration of fxy dx over minus infinity to infinity. It gives us the marginal PDF of y. For example, consider the following PDF. fxy is equal to 3 minus x minus y, where x is greater than or equal to 0 but less than or equal to 1, and y is greater than or equal to 0 but less than or equal to 1. So the marginal PDF of the joint PDF are fx is equal to fxy dy over 0 to 1 is equal to integration over 0 to 1 into 3 minus x minus y into dy. And this comes out to be equal to 3y minus xy minus y square by 2 given the values from 0 to 1 and is equal to 5 by 2 minus x. Please remember here x is greater than or equal to 0 but is less than or equal to 1. Similarly, fy is integration of fxy dx over 0 to 1 and this means we substitute the values and we get integration from 0 to 1 of 3 minus x minus y dx. On simplification, we get this equal to 3x minus xy minus x square by 2 given value from 0 to 1 and is equal to 5 by 2 minus y, where x is greater than or equal to 0 but less than or equal to 1. Statistical independence. Two random variables are said to be statistically independent if and only if fxy is equal to fx into fy. That is to say that the joint probability distribution function can be expressed as the product of marginal probability distribution functions, or joint density function can be expressed as the product of marginal density functions. Any probability distribution can be summarized in terms of its characteristics known as moments of the distributions. Most important moments are mean and variance. Mean. Mean, also known as expected value of a discrete random variable, expected value of x or ex can be written as follows. Ex is equal to summation x fx, where summation is over x. It is a product of the x values with its corresponding discrete probability distribution values, or PDF. Summation of x means summing over all values of x. The expected value or the mean of the probability distribution is obtained by summing the product of various outcomes with the probabilities. The probabilities here serve as weights. Similarly, the expected value of a continuous random variable x, ex, is defined as expected value x is equal to x fx dx integration from minus x to x. Use of the integration sign instead of summation sign is the only difference between the expected value of continuous and discrete random variable. We can show the same with the help of an example. Example, estimate expected values of discrete random variable x from the given data. The values of x are minus 1, 1, 2, 3. The corresponding fx is 0.25, 0.11, 0.25 and 0.39. Therefore, expected value ex is equal to summation x fx over x, and substitution of these values gives us this equal to 1.53. Example. Consider the following PDF function. Fx is equal to 1 by 9 x raised to power 3, where x is between 0 and 3, which means x is greater than or equal to 0 but less than or equal to 3. Then expected value of x is equal to x fx dx integration over minus x to x. This is equal to integration from 0 to 3 x into 1 by 9 into x raised to power 3 dx. This comes out to be equal to 1 by 9 into x raised to power 4 upon 4 given the values from 0 to 3. On substitution, we get this equal to 2.25. Variance. Let x be a random variable whose expected value ex is equal to mu. Now variance can be defined as the spread of the x values around its mean or expected values. It basically explain how far away individual x values lie from its mean values. And this is expressed as follows. Variance of x is equal to expected value of x minus mu whole square. Variance is defined as follows. Variance of x is summation of x minus mu square into fx. Summation is over x. If fx is a discrete random variable. This is equal to variance of x is equal to x minus mu square into fx dx, integration from minus infinity to infinity if x is a continuous random variable. In terms of expectation, variance can also be written in the following three ways. Variance of x is equal to expected value of x minus mu whole square. Variance of x is equal to expected value of x square minus mu square. Variance of x is equal to expected value of x minus expected value of x whole square. Now, variance can also be defined as the weighted average of the square of the deviations taken from the mean, where the probabilities act as a weight again, given the variance of the probability distribution. The table below shows the methodology of the calculation of mean and variance of a probability distribution. In this table, you find we have the outcomes x ranging from 0, 1, 2, 3. We have the corresponding probabilities 1 by 8, 3 by 8, 3 by 8, 1 by 8. We have the product of these xi with pxi, and we have these values 0, 3 by 8, 6 by 8, 3 by 8. And the summation, or let us say the mean, is equal to 1.5, which is your expected value. Similarly, the variance is xi minus mu square into pxi, and we have the cell values which on summation in the end or the last cell gives us sigma square variance equal to 0.748.
So what have we learned? Let us summarize it. We have learned that a random variable is a rule that assigns a number to each of the outcomes. We have learned that fundamentally the random variables can be classified into two categories, discrete and continuous. A probability distribution relates each possible outcome of a given experiment with its corresponding probability of occurrence. We have also learned that the cumulative distribution function helps to compute the probability that the observed value of x will be at most x for some given value of x. So let me remind you, we have learned that capital X is used for the variable, whereas small x is used for the specific value of the variable. Investigators can use more than one random variable in the experiment situations or in experimental situations. In such cases, the joint probability mass function, written as joint PMF, is considered. In relation with the joint probability distribution function, fxy, fx and fy are called marginal or individual probability density functions. Two random variables are said to be statistically independent if and only if fxy is equal to fx into fy. I am sure you would recollect this small f is written for continuous distribution and is known as density function. We have also learned that any probability distribution can be summarized in terms of its characteristics known as moments of the distributions, most important moments being the mean and the variance.